function. It doesn't require the use of calculator, nothing about what we did for the last month at all. Okay. Firstly, this is only a chapter relevant to discrete random variables only. Okay. So the key is to be able to express a probability distribution function or a table into a polynomial. Okay. So what do I mean by that, right? Okay, the notation for PGF tends to be like this. Let's say PGF X, then in T, or GX T, okay? And by hardcore definition, right, it actually means this: summation probability X is equal to X, which is something that you are very used to already, right? And then T to the power of X. So what does this T refers to, right? This T is aka a dummy variable. What does it mean by that? It's simply a variable that doesn't mean anything, but it's put down there as a placeholder between the probability and the outcome. Because the letter X has to be reserved for the variable, the actual variable that we are interested in studying. Okay. So what do I mean by that, right? So this particular summation, to be expressed in more concrete terms, actually means like this: probability X is, assuming X starts from 0, T to the power of 0 plus okay. So again, what does all this chunk really mean, right? So to give you a more physical example, would be something like this: if the discrete random variable X has got outcomes 0, 1, and 2, or 3 to be precise, okay? Purposely skipping a 2, and then with probability 1/3, 1/4, and 5/12 like this. Okay, its PGF will be expressed as such. So the short form tends to be G subscript X, then T. Okay, the subscript actually refers to which variable you are constructing for. Then at the end of the day, this polynomial or the function has to be got to be in terms of T, the dummy variable. So it will be like this: 1/3 T to the power of 0 plus 1/4 T to the power of 1 plus 5/12 T cubed. Okay, so this is the probability generating function or polynomial describing this particular discrete random variable. Can follow so far? Can see the pattern? Okay, so there are a few things that you will see how I did it. Okay, so you may ask, then how come do I want to simplify this to write as 1/3, then plus 1/4 T plus 5/12 T cubed, right? My answer to you is no. I prefer to keep it in this form. Why? Because I can see the number 0 and 1 respectively. Okay, when you see 1/3, it doesn't really trigger the thought of 1/3 T to the power of 0. Same goes for 1/3 T. You may get too distracted to see that there's actually a 0 and 1 here respectively. Okay, so my personal preference is to keep it in the blue form. Okay. So what about other powers like t squared, t4, t5, or t to be negative? They simply do not exist because if you look at the table, x cannot possess those values, hence the coefficients are 0, means improbable at all, impossible. Okay, that's it. So as a basic rule of thumb, PGF, right? The dummy variable t is meant to separate the coefficients and the outcome, which are meant to illustrate, convey two separate information. Coefficient refers to the probability. Power of t refers to the outcome. Okay, can? So this is how a PGF is constructed first. And somehow there's a bit of a, and then we realize that there's very elegant information contained inside the polynomial instead of the table. Okay, so how is it so, right? So why do you want to use it, right? It's because it actually creates a very good mechanism to construct addition of variables. So what do I mean by that? For example, if you have x 0, 1, 3, just like we had just now, probability 1/3, 1/4, 5 out of 12. Then you have another table, you have another variable y. Y could be 2 or 3 with probability 1/3, 2/3. Okay? In the paper 1 and paper 2 situation, if I ask you to go and construct the probability table for x plus y, right? You are going to do something like this. Then you will brainstorm the cases. Then you will say this is 0, 1, 2, 3, 4, 5. Okay? Probability. And then you will be brainstorming the numbers one by one, right? Multiplying the probability together, assuming x plus y, x and y are independent. Okay? And so you will see, okay, this seems like a logical way to do this question. Then, okay, let me just construct the PGF for x and y first. So the PGF for y is 1/3 t squared plus 2/3 t cubed. Then the PGF for x is 1/3 t to the power 0 plus 1/4 t to the power 1 plus 5/12 t cubed. Okay, PGF of x, PGF of y. To actually understand how the x plus y operate, right, the key is simply to multiply the PGF together. And this creates a very simple mechanism for us. So if I were to just multiply the PGF together, I will get like 1/9 t to the power 2 plus 2/9 t to the power 3. It should be 3. Then plus dot dot dot. If you see the final stuff will be 5/36 t to the power 5 plus 10/36 t to the power 6. Okay. Then with this newly constructed PGF for the variable x plus y, right? We will be able to construct the table like this easily backwards. Can see? Can understand? Yes, no, yes?
Yeah.
Okay. Okay. The thing is, this thing here is only applicable when you're doing addition of variables. Okay. Why so, right? Because when you are you will see that the process of multiplying the polynomials together, right? What really happens? You are adding up the powers, correct? And by adding up the powers, you are actually adding up the variables because power refers to outcome, correct? If you take this term, multiply by this term, it's actually 2 plus 0 in terms of the power, and that is the outcome of x plus y, which is 2. And then by the multiplication process also neatly created the multiplication between the coefficients, which is the probability. Understand? Yes, no, yes, okay. So this mechanism is kind of not so useful when your x and y has got only 3 outcomes and 2 outcomes respectively, right? So you can easily do you may think that I might just use do the brainstorming method, and that is correct actually. However, in the actual situation, if your x and y contains 10 outcomes each, right, then you will go nuts doing the brainstorming because there will be a total of 20 different outcomes in your table for x plus y, which is not very legit. However, if you turn them into polynomials, we can actually use computer to calculate or to construct multiplication of polynomials very easily. Okay, and then from the polynomial, we can generate the probability table easily again. So when your x and y have got dozens of possible outcomes, right, the multiplication of PGF becomes a very swift operation. Okay, you cannot program a computer to understand a table like this, and then how they interact to create a new table in general. Okay, or you'll be quite tedious. But we can actually program a computer how to extract the polynomial from the table and then to do a multiplication of polynomial within seconds. Okay, and that is why if you think in terms of computer, this PGF chapter is very useful at this juncture. Okay, and but the unfortunate thing is this elegant result, right, is only applicable for addition of variables. Because if you have subtraction of variables, theoretically you can do division of PGF, which will create But the division of PGF, when you have a polynomial divided by a polynomial, the powers don't really subtract each other on a like-for-like perspective, right? Because you need to actually do long division of polynomial and then things will get really, really messy. So unfortunately, this result is only applicable when you're doing addition of variables, okay? So remember, the multiplication mechanism creates a very elegant movement to create this and this, okay? That is the first key aspect of PGF, okay? So we usually, we write something like this. The probability generating function of the addition of two variables, like this, still the dummy variable t, of course, is simply the multiplication of their individual PGF. Okay, the across the board, the dummy variable will always be t. You're not going to use a different letter for a different function. Okay. Okay. So also, it becomes a very easy situation to construct the expectation of a variable. So what do I mean by that? So the expectation of the variable, right, is simply to differentiate the PGF with respect to t first, and then substitute t to be 1. Okay, so this formula here will allow you to construct the expectation of calculate the expectation of a variable very quickly, because you know how to differentiate something, a polynomial very well, and sub t to be 1. In fact, you can use the GC to do it for you. Numerical derivative at a point, then key in the polynomial, then let t to be 1. So how come this formula is legit, right? Imagine, again, if you use the same example that we had just now, you have x. Let me just change the variables a little bit. So 1, 2, 3 then. So if our probability is now 1/3, 1/4, and 5/12. In your usual paper 1 and paper 2 situation, to calculate the expectation for x, you will say 1/3 plus 2, 1/4, 3, 5/12. Okay. So the key now is to be convinced that this formula here actually creates the same mechanism as this. Okay. How does it do it, right? So the first thing is obviously to construct the PGF first. So the PGF of x, gxt, is equals to 1/3 t to the power 1 plus 1/4 t to the power 2 plus 5/12 t to the power 3. So we need to differentiate first, right? So differentiate with respect to t. You can see what will you get. So gx, differentiation means power comes down, then subtract 1 from the power, right? And the mechanism of doing this creates the sum product between powers and between outcome and probability. Correct? You can see that the mechanism of this thing is exactly these things here. Okay, so by executing the differentiation process, right? And the power comes down, and power represents outcome, and this outcome is multiplied with the coefficient, which is probability, and the sum of these things creates the expectation formula. So now what's really bothering you is the existence of t throughout, right? So how do you neutralize its effect? Is to let t be 1 right now. You obviously cannot let t be 0, right? If you let t be 0, everything goes to 0 right now. So if you let t be 1,
Sir.
yeah.
Why is it t to the power 3 minus 2?
T, where was t minus 2?
The gx prime t, the equation that you have.
Yeah,
Why is
minus
it
2?
t to the power 3 minus 2?
Oh, sorry, minus 1.
Oh, 3 minus 1, okay.
Yeah, good, thank you. Okay, so if you let gx, if you let t be 1, the effect, the presence of t gets neutralized, and then what you have left is the expectation formula actually. So 1/3 plus 2, 1/4 plus 3, 5/12. And then that is the same as this thing here. Okay, understand? So at least you must be aware that this formula is legit. Okay. this expression here will be inside the formula sheet for you. Okay. So again, what's the use of this, right? So you kind of feel that the table is more useful also, right? And the answer is yes, from a polynomial perspective. Okay, if you have a polynomial versus a table, you can do both pretty well. Okay, assuming that you have 5 or less cases. Even for a computer, asking a computer to do a sum product of these things versus asking a computer to differentiate a polynomial versus and put t to be 1, right? The timing wise is not much of a difference to play any significant importance to you. However, later on you will see that there are some situations where a PGF of special distributions, right, is not in a polynomial but into a compressed form. And under those situations, you will not be able to calculate the expectation as well as you do a PGF formula then. Okay. So for now, just accept it as it is and be convinced that the mechanism that we are providing here actually works. Okay. Okay. Any questions on this so far first? Yes, no, yes. Okay with this? Okay, yeah. Okay. So the next mechanism is variant. Oh no. Okay. Actually, there is also a formula to calculate the variance, which I will not prove. It's also inside the formula sheet, and it's this. So if I have a PGF of a formula of a distribution of a variable, right? The variance is calculated as such. G double prime 1 minus G prime 1 minus G, sorry, this is plus, minus G prime 1 squared. Okay, so I will not prove this formula also. So this thing here actually refers to your, this is your EX squared. Okay, this thing here is your EX squared, like this. Okay, so as a result, we can actually calculate the variance pretty quickly also without going through the bothersome stuff that we used to go through in tables 1 and 2. Okay, so this side trick formula for variance and EX are inside the formula sheet for you. Okay. What is the really requirement to calculate the next usefulness of a PGF, right? Is it actually gives us a quick way to obtain or mathematical way to obtain the probability of any outcome again. Okay. So what do I mean by that? Okay, if you have X, 2, 3, okay, 1, 3, 4, then 1, 3, 4. Wait a minute. 1 differentiate 2 times. Okay, 1, 3, 4. Then probability is 1/3, 1/4, 5/12. Okay. Theoretically, if you look at the table right away, if I want you to construct to tell me what is the probability of 3, you will say, oh, it's just 1/4. Okay. But in the, and this is a very handy situation, of course. But in the real world, your variables wouldn't be nicely presented to you in a table form, right? So is there a mathematical way that we can ask a computer to construct or work on a function such that we can calculate the probability of any outcome? And is this, okay? In the world of PGF, the formula is this. Probability x is equals to n is you will differentiate the function n times divided by n factorial, then let t be 0. Okay? If you apply this mechanism onto the PGF of this variable x, it should output you the number 1/4 at the end of the day. Okay? So we will see how come this formula has got 3 components, right? Differentiate n times, then divide by n factorial, then let t be 0. How they each play a part in isolating the number 1/4 at the end of the day. Okay? So the PGF for this variable is simply 1/3 t to the power of 1 plus 1/4 t to the power of 3 plus 5/12 t to the power of 4. Okay, so I'll just call this g, all right, for simplistic. Okay, so I need to differentiate this expression 3 times first. So you will see g prime, this will give you 1/3 plus 3/4 t squared plus 20/12 t3. Okay, So differentiating 2 more times, g double prime is equal to 0 plus 6 over 4 t. Okay, I should not have done that. Okay, should not have evaluated. So just now was, okay, so you will have a 2 and a 3 and a 1/4, right? T to the power of 1 plus a 4 and a 5 and a 5 over 12 T2. Okay, so differentiate a third time. I will have a 1, a 2, a 3, a 1/4 t to the power of 0 right now, plus a 3. Yeah, I did something 4, 5, 4, 5, 3. Okay, sorry, yeah. There's a mistake in the differentiation just now. Plus, then here is a 3. Okay, then if you did, so I will have a 2, 3, 4, 5 over 12 T1 right now. Okay, after differentiating 3 times, I will get to this stage round. Okay, so you can see that after differentiating 3 times, right, what has happened? Remember, right at the start, my goal was to go through a series of steps to isolate this particular number, right, 1/4. Okay, which is the probability of x is equal to 3. Okay, by differentiating 3 times, right, the terms before it will have all disappeared, correct? Because in terms of polynomial ranking, their powers are below 3. So if you differentiate an algebra 3 times, anything whose power is below 3 will have disappeared by now already. So by this mechanism, the first mechanism of differentiating n times here, will have ensured that all the terms before this term gets cubed off. Okay, so far? So the terms that remains are the terms that I seek, and the terms be after it. Okay, so now the next move is to let t be 0. Letting t be 0, what purpose does it serve? The term that I'm looking for is actually here. It's already t to the power of 0. So letting t be 0 plays no part at all. But letting t be 0 allows me to queue off the terms after it. In particular, this guy. Okay, so if you let t be 0, you're going to get 1, 2, 3, 1/4. That's all right now. Okay, plus 0. Okay, so the terms after it has been cubed off this particular guy. Okay, so that is the whole purpose of letting t be 0. Understand so far? So after that, you must divide by 3 factorial. Okay, and then the purpose is clear right now, right? So g prime 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 0, 3 factorial is equals to 1/4 then. Okay, because by dividing by 3 factorial, you'll be neutralizing this 1, 2, and 1, 2, 3. Okay, where did this 1, 2, 3 came about? Because you differentiated 3 times, right? In the process of differentiating 3 times, you will have brought down the 3, brought down the 2, and then brought down the 1 respectively. Here, 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 and here. Okay, they all came down or were created as a byproduct of differentiation. So if you choose to divide by 3 factorial, you'll be neutralizing their presence, hence isolating the number 1/4 at the end of the day. And that is the mechanism that will allow you to extract the number 1/4 from the table right at the start. Okay? Can follow so far?
But isn't that a bit circular because you already know what it is?
Okay. This is built on the assumption that you know the table or values right at the start in your face, right?
Yeah.
You get what I'm saying?
I guess.
Yeah. Okay. So it won't be the case in some of the PGF question. We won't give you the table, but we will just give you the function of the PGF. Even though I display all my PGF in a polynomial form, right? It's not always the case. Okay. Some of the special distribution functions, their PGF can be compressed into a closed form function like exponential function or a trivial function even. Okay, we will see this in later on. Okay, but I'm just giving you all this expression, all this formula, right? So that you are convinced that it actually works. And how come the formula looks so complicated first? Okay, so just be aware that at least for this formula, right, each of them plays a role in isolating the information.
Okay,
You get
Wait,
what
but
I'm saying?
sir, isn't like 0, if you say t is 0, right? Like then 0 to the power of 0 is math error, right?
No, 0 to the power of 0 is nothing. For which one? At the last step here, is it? When I t to the power of 0 by default is already equal to 1 already.
Huh?
So t to the power of 0 is already equal to 1 already. Anything to the power of 0 is equal to 1 because of indices.
Oh, okay, yeah.
So there's only to let t be 0 already. This guy practically disappears already, okay?
Oh, okay.
So there's no point in letting, it's more like to kill off this guy only, the next guy actually.
Oh.
Okay. So clearly you all feel that when I have it in a table form, everything feels stupid, right? Why would anyone go through all this? Even if you use a computer, you're not going to ask a computer, why will you program a computer to differentiate something 3 times for you to go through all this nonsense, when you can easily ask the computer to reference West Street and then tell me the corresponding number below it. I agree with you, okay? But sometimes information won't be embedded in the table form, as we will see later on, okay? But for now, okay, then the good thing is this thing is still inside the formula for you, okay? Formula sheet for you. Okay, Ken? Okay. So now is a known fact regarding to the world of PGF. If you want to look at two tables, right, X and Y, you want to say that they are the same distribution or whatsoever, you must look at the table, then compare every single column that they have the same outcome and same probability, okay? So only then you can say that they have the same distribution, same mean, and same variance. Two distributions may have the same mean and variance, but it doesn't mean that they are the same. Two variables may have the same mean and variance, but doesn't mean that they are the same distribution. But if you look at it from a PGF perspective, if they have the same PGF, then they must be the same distribution. Okay, and that is a very important fact that we will be using for the standard distributions later on. Okay, because when you have a binomial, Poisson, or whatsoever, right? If you look at your questions before, when they say, can you try to argue that X follows a binomial, X follows a Poisson, right? It is always that you need to argue that X follows the assumptions of a binomial or Poisson, like, oh, the trials are independent, success or failure, then n trials, odds of success is a constant across all trials, that kind of arty-farty stuff. There wasn't really a mathematical way to justify it. So the PGF will give you a mathematical way to justify why X follows a certain distribution later on. Okay, so we will come back to this later on. Okay, let me think. Okay, so with regard to a standard PGF, this is it. Okay, you must know the results of a PGF and in particular the expectation and how to find the probability of any outcome first. Okay. So what are the standard questions that you can expect from here, right? Is to find a substitution. We make a variable go through a transformation first, and then you calculate the new PGF. Okay. So I will give you two different methods that you can use to solve this kind of situation. So for example, we will give you X first. Okay, X is again 1, 2, and 3 with the probability 1/3, 1/4, 5/12. So when we say, hey, there's a new variable y, so can you tell me what is the PGF of y? Okay, so this is one kind of transformation you can expect, translation plus minus something. So a technique that you can do is to construct the probability table for y. You will create y is 4, 5, 6. And take note that there's no change in the probability, because for y to be 4, x is to 1. For y to be 5, x is 2. So you will still have 1/3, 1/4, 5/12. So this is constructing the table from scratch. So if you need a point of reference, x is still going to be 1, 2, and 3. Then from here, you just need to simply say PGF G, Y, T is just 1/3 t to the power of 4 plus 1/4 t to the power of 5 plus 5/12 t to the power of 6. Okay, know how to construct the table like this, or at least think about how the table works like this for yourself will do. Okay, because this may not always be applicable because the table may not be present in the question. Okay, like this, that's all. What is the second method? the second method is to work from the definition of a PGF. So we may just give you the probability, the polynomial for a PGF in your face right away. So we may say GX. Okay, so from here we will just say, we will just say GYT is equals to probability. I should not do this. Y is equal to 4, T to be 4 plus probability Y is equal to 5, T to be 5 plus probability Y is equal to 6, T to the power of 6. Okay, this is by definition the construction of a PGF for variable Y, and the odds of Y to be 4, 5, and 6 are simply the odds of X to be 1, 2, and 3. So you will just be equals to probability X is equals to 1. T is still 4, okay? Because the outcome is focused on Y. So the plus okay, 6, sorry. Okay, so what does this blue and red statement really mean, right? It means that the odds of Y is 4 is the same as odds of X to be 1, 2, and 3 respectively. But the outcomes are always going to be 4, 5, and 6, simply because we are actually aimed at constructing the PGF of Y right now and nothing else. The PGF of X doesn't come into play here, but rather we are just focused on constructing the outcome of X doesn't come into play here beyond telling me that Y can only be 4, 5, and 6. Okay, then from here you can actually construct the fill in the blanks and then you get the same answer right away. Can follow this method? Can understand what am I doing in these two places here? It feels that these two feels that they are very similar, right? But there will be a stark distinction depending on whether the question gives you the table when the time comes. That's all. Okay. But for now, just be aware that whatever I'm writing seems to make sense to you. That's all. Yes, no, yes. Okay, Ken?
Yeah.
Okay. Edward, you okay with this?
Yeah.
Okay. Then there is one more method. It's called the addition of variables is a multiplication of PGF. Just now I mentioned, right? Addition of variables means it's multiplication of PGF. Right? So actually from here, I can actually, okay, I'll just sacrifice this portion. So I'll just, the PGF of Y is actually the PGF of X plus 3, right? Since Y is X plus 3. And this is actually an addition of two things. Addition of two things means it's the multiplication of their individual PGF. So this is actually equals to GXT, which we can construct easily from the table before, times the PGF of the constant 3. Okay? So this is something that you can take easily, multiply by. Now, what is the PGF of the constant 3 by definition? Remember, PGF means coefficient is probability, outcome is the power, right? If you look at the constant 3, what is the probability of 3 being 3?
1.
1.
And that is the PGF of the constant 3. So the PGF of 3, right, is actually 1t cubed, okay? And then if you multiply with the PGF of x, you will get the answer here again, okay? So it's actually taking t cubed multiplied with every single term in the PGF of x, which kind of makes sense, right? When you multiply t cubed with every single term in the PGF of x, you are increasing the powers of the terms by 3, which is this plus 3. Hence 1, 2, 3 became 4, 5, 6, that's all. Understand? But I just want you to see that all three methods or all three writing style or thinking style seem to point towards the same facts regardless, okay? It's either you are constructing from the table from scratch again, or you are constructing the PGF of definition again, or you are constructing the PGF by making use of the multiplication of individual PGF and knowing how to construct the PGF for a constant. Okay, because this is the one thing that will get students stumped in the actual exam. They just cannot figure how come a constant PGF will be like this. But if you go back to the definition that coefficients represents probability, power represents outcome, so this will make sense to you. Okay. Okay, this is not good writing.
Can you explain the third method again, please?
Okay, give me a minute. Okay, do you understand that? Do you understand what I wrote here first? The PGF of an addition of variables is the multiplication of their individual PGF.
Yeah.
Okay, so what is the PGF of 3, the constant 3? Do you agree that is this thing that... Say again?
3t to the power 0.
Okay, you are saying it's 3t to the power of 0?
1t to the power 3.
Yeah, 1t to the power of 3, understand? And that's why, if you multiply, that means if you multiply 1t to the power of 3 with the PGF of x, you will get a PGF of y. Okay, and then, which is actually this in disguise. Understand?
Yeah, okay, thanks.
Okay, which means that you're multiplying t cubed to every single term in the PGF of x. Multiplying t cubed to a polynomial means you're just adding 3 to the power, that's all. Okay? Okay, let's take a few minutes break on this first. Let me queue off this Zoom meeting first. Okay?
Okay.
Yeah.